continuous fraction. First of all, let me, before we introduce continuous fraction, I would like to motivate why we are studying continuous fraction. So if you recall the last time when we computed the Padé approximation of the exponential function using a third degree polynomial in the numerator and second degree polynomial in the denominator, we obtain this result for the exponential function. As you can see, if you try to compute the number of addition and multiplication in the numerator and the denominator, you can see that the number of addition and multiplication will be very large. If you recall, for a polynomial written in this canonical form, we can see that the number of addition is exactly 3, which is the degree of the polynomial. The degree is 3. You have 1, 2, 3 addition. But the number of multiplication, if you recall, it should be of the order of n squared. That is the order of 9. Right? Because n is 3, n squared is. When you say the order, it means it's big O of n squared, which is the degree of the polynomial here in the numerator, similarly here. But if you want to know exactly the number of multiplication for a polynomial of a certain degree will be exactly, if the degree is n, it will be n into n plus 1 by 2. And addition is exactly n. So since our n here is 3, it will be 6 in total multiplication in the numerator, because this will be 4 by 2, 2 times 3, 6. And here we have 3 addition for the numerator only. So if we do the same thing here for the denominator, the number of multiplication will be, this is 1, it will be 3. We have 3 multiplication because n is 2 by 2 is 1, and 2 plus 1 is 3. That's multiplication, and addition is 2. Addition is 2. So the total, so if you compute the total for this one, if you try to compute the total number of multiplication, we can see that it will be 6 plus 3, which is 9. There will be a total of 9 multiplication, and the total number of addition will be equal to 5. That is 3 plus 2. 3 plus 2. Okay, so we have 9 multiplication in total and 5 addition in total, theoretically. Okay, but recall that for a polynomial, we can reduce it using the nested form to n addition and n multiplication, n addition, n multiplication. So if you use the nested form in the numerator and nested form in the denominator, so if you use the nested form, so the total nested form will give us 3 will be 3 plus 2 equal to 5, and addition will be the same. 3 plus 2 equal, what have I done? I said the nested form. Oh, yeah, yeah, I add the numerator and the, okay. Addition, similarly, we have 3, 2, 5. So you can see that for multiplication, we move from this to that. And addition is still the same, no change. So the nested form here is reducing the number of multiplication. So this is if we use the nested form in the numerator and in the denominator. Okay, but we can use continuous fraction for this to reduce the number of addition, to reduce the number of multiplication, because as you can see here, the total number of multiplication is 9. So we can reduce that by using something similar to the nested form, but particularly intrinsic to rational function. So that is what continuous fraction is all about. But before diving into continuous fraction for rational function, we will first introduce continuous fraction for real numbers in order to set up the stage for a better understanding. So in the definition, continuous fraction is just an expression that can be written in this form, in one of these forms. You can have more, but in our particular case, we assume that we are dealing with a real number that is a rational number. If R is an irrational number, we are sure that our continuous fraction will be finite. Otherwise, we can have an infinite representation of this form. It will continue forever. But we want to stop because for our case, we are dealing with the rational function, meaning that if we perform continuous fraction, we have a finite number of terms in such a decomposition. So that's why we are going to use just finite expansion in our continuous fraction. So in this definition, A0, in all this expansion, from the second one up to the last, A0 stands for an integer, right? And the remaining terms of the expansion, or the series, if we call the A case to be the series, from A1 up to AN, they are all positive integers except A0. So meaning that if your original R is a negative number, A0 will carry that negative sign, and the remaining A1 up to AN will be positive. So our concern here is mainly about the algorithm. If we are given a rational number, because only rational number will give us a finite number of terms. If we have a rational number and we want to perform such a decomposition, that is decomposition in the form of a continuous fraction, we will follow the following algorithm. First of all, we identify what is the real, the integer and the fractional part of our real number R. So if you identify the integer part and the fractional part, we draw a table where we will represent the real number in the first column. So R will be here in the first column, and then in the second column will be the integer part, and the third column will be the fractional part. And the fractional part is just the difference between the original number, real number, minus the integer part. That will give us the fractional part. And then we compute this reciprocal, which will be another real number, and we start over the process. And we stop only when the fractional part is 0. Then we stop. So that is the algorithm that we will follow here. And all the entries in the integer part here, all the terms in the column representing integer part constitute our sequence. So this will be A0, A1, A2. Right. As you can see here, 1, 3, 2, 1, 3, 2. So this will be our A0 and then A1 and A2. So we have A0 plus 1 by A1 plus 1 by A2. So the last denominator will be this expression here, the last entry in the integer part column. So that is roughly speaking the procedure. So let's look at a few examples. First of all, we have 9/7, and we have the mixed fraction. Written in this form. So how do we write 9/7 in the form of a mixed fraction? 9/7. We can write 9 as 7 plus 2 by 7. Now, if we split the numerator into 2, I mean the fraction into 2 parts, so 7 by 7 will give us 1 plus the second one will give us 2 by 7. So you see that this is 1 plus 2/7, which in the mixed fraction form is written as 1, 2, 7. So it's always better to write our real number as a mixed fraction. It would allow us, because from here we know already what is our, this is our integer part, I, and this is our fractional part. So it's read directly without any ambiguity. Okay, so once we have it, we draw the table as I mentioned previously. This is our original, the very first expression of R is given by this mixed fraction form. And we have the integer part 1 and then the fractional part 2/7. And then we take the reciprocal of this, which is 7/2. 7/2, we can do exactly the same thing and write it as 6 plus 1 by 2. So this will be 3 plus 1/2, which is 3/1/2. So this becomes that. So that's our reciprocal. It becomes our new integer, our new real number that we put in the real number column. That reciprocal, we repeat it here, and we start the process over. That is, since it's in mixed fraction form, we have integer part and then the fractional part. So we write in the corresponding entries, and then we take the reciprocal of this, which is 2. 2 is a whole number, so we can take it. We are sure that once we get the whole number like this, the fractional part will be 0, because here we can see that the fractional part already here is 0, right? Because it's a whole number. So that is our integer part. So we put it there, the integer part will still be the same, the difference gives us 0. Then we stop and we collect our sequence in this column. So this is our A0, A1, A2. So this is the sequence, and therefore we can write it as a continuous fraction, A0 plus 1 by A1 plus 1 by A2, which is exactly this. So if we do exactly the same thing with the next real number, we have integer part, fractional part, and then we take the reciprocal, 200 by 49, we can write it as a mixed fraction. So we copy that here and we split into 2. We have the integer part, fractional part, take reciprocal, that would be 49 by 4. Integer, mixed fraction representation is 12 and 1/4. So we copy there, we have 12 integer part, 1/4 the fractional part. We take the reciprocal is 4. We are sure that very soon. Since it's a whole number, the fractional part is 0. We put it there with this integer part, fractional part is 0. We stop, and then we collect the entries here, A0, A1 is 4, A2 is 12, and A3 is 4. And then we write exactly that. 3 plus 1 over the longer bar. And then below the bar, we proceed 4 plus 1 over another bar. Under that, 12 plus 1 by 4. And that is it. This is a continuous fraction expression. So we can do that because we are dealing with rational numbers. So that's why we have a finite sequence, right? Finite number in our expansion. So now that we are done, we understand the method, we can now apply it to a rational number, because this is a second degree polynomial. This also is a second degree polynomial. Because it's a second degree polynomial, we want to, the first thing that we'll do, we'll perform a long division. We know that if we divide second degree polynomial by another second degree polynomial, we have a quotient that will be the quotient here will be a constant term, because it will be a constant term. I can say here constant term. Will be a constant plus a fraction. Let me call that P1 by Q1. And the second term here will be in such a way that the degree of Q1, this one will be greater than the degree of P1. In such a way that, because now this is like a fraction, we can perform the long division and obtain a similar sequence as like this one, because we know that we have an irreducible fraction or rational function. So let's do that. So we perform the long division. So this is our numerator, this is the denominator, meaning we have the dividend, which is this one. This is our dividend, and this is a divisor. So we have the dividend and this one is the divisor. So we can we write it. So we take our divisor here, and here we write our dividend. Okay, so this will be the quotient. And we start the division. So we take this expression. We start with the first term here. So 3x squared divided by x squared is 3. So the result, we write our 3 there. And then we take that 3, we multiply the divisor and write it under the dividend. So 3 times 3x squared is 3x squared. 3 times x squared is 3x squared. 3 times negative 2x is negative 6x. We write negative 6x, and then 3 times 1 is 3, obviously, and then we subtract, so that's why the sign will change, negative, positive, negative, and then we add, that is, we take this, subtract that one. So if we perform that, 3x squared minus 3x squared is 0, and then here we have 0, right? And then with this one, then 0 plus this 6x, because it's actually 0 minus 6x, which is 0 plus 6x. The result is 6x. And then minus 4 minus 3, which is minus 4 minus 3. It is negative 7. We write it there. And we are done. So this will be the remainder. This is the remainder. So once we have the remainder, we know how to write the final result. So this fraction, which is this divided by that, what would that be equal to? It will be equal to the quotient here, right? Which is the constant term I mentioned here. That is our quotient. So we write the quotient So we have the quotient plus the remainder divided by what? Divided by the denominator, right? Because actually, how do we get this? We can write the dividend, which is this one. This one is our numerator, right? We can write our dividend. We can use this the relationship or the relation that connect the dividend to the divisor, the quotient, and the remainder. So if you write the formula, we know that, okay, let me write it here. We know that dividend is equal to the divisor. I will just put div for the divisor times the quotient. I will just write co plus the remainder. We'll just write rem for the remainder. Now, and what is our R? R is just the dividend by divisor. Now, if I divide this again by the divisor, I will get my Rx. So Rx will be the dividend divided by the divisor Now you see that if I cancel this, I'll get the quotient. So this will be equal to the quotient plus the quotient plus the remainder by the divisor. So what is the quotient here? The quotient is 3 plus the remainder, this one, divided by what? The divisor. And the divisor is what? This is our divisor. Right? Divisor is this one, x squared minus 2x plus 1, which is actually x minus 1 squared. Right? That one. It's exactly the same. And this is what I call P1 and Q1. Now, if you look, you see that the degree of the numerator is less than the degree of the denominator. I think I wrote it somewhere here. Yeah. Degree of the denominator is greater than the degree of the numerator. Right. So, and that's exactly what we have here. And because of that, we can perform our continual fraction process. Now, if you do that, remember that if I have that, I have to identify the terms. But in our case, this is our, because this is like the integer part, and this is the fractional part. You can really see that this is a whole part, or it can be a polynomial itself, because remember that this is a fraction. Rational function is like a fraction, and this one is like a whole number. It can be a polynomial, it represents a whole number, and then we have another a ratio of polynomials, which is like another rational function, but in this case, the degree of the numerator has to be less, right? Then it will appear actually to be, in this form, it will be the fractional part. Now we take the reciprocal of the fractional part, as you remember, this is a reciprocal. Once we have the reciprocal like this, we can use this one and reperform the long division, right? Now, if you perform the long division, so this is the term that we are going to operate upon. So if you take that, you see, as you can see, we can perform a long division to this. So this will be what? Numerator, denominator, or we can say dividend, divisor. Dividend, divisor. So this is our dividend here, and this is our divisor. We put it there, we perform the long division. As usual, what we can say, we take this, we divide by that, right? But you can, as you can see here, this is a first degree I mean, this is first degree, that is second degree, so there will be x and a factor, and that factor will be the reciprocal of that, 1 by 6, in such a way that if I multiply, I take this, I multiply by that, it will give us x squared, right? And then we take also this still, and we multiply by that, it will be negative 7 by 6x, which is that. Obviously, we multiply by negative because we are subtracting, so minus, then we distribute a negative sign throughout, then we get this. We add the 2, you can see that x squared will cancel out with this one, and then this one and that one will give us negative 5, 6x. And then this one, we carry the 1 down here, and we repeat, because this will be like our dividend. So we pursue the division. So if you want to divide, you can see that you have, this is x and this is x, right? So the question will be a constant term, which will be what? Which will be this divided by 6. So if we divide this by 6, it will be negative 5 by 36, because 36 is 6 by 6. So we put that's our quotient, and then we multiply the divisor by that, and it gives us, if we multiply throughout, we get this, and then that gives us this, and then we subtract that, we multiply by the negative sign, we add them up. So this and that will cancel out, and then we have 1 minus 35 by 36. That will give us 1 by 36, and this is our remainder. Now that we have the remainder, we can do exactly what we did here. So we rewrite this as what? So this will give us the quotient plus remainder by the divisor. So what is the, we can see it. So this will give us the quotient, which is this one, and this is the quotient, plus the remainder, which is this one, divided by the divisor. That. Now at this stage, we can take this, substitute back into the denominator. So that will be 3 plus 1 by, we substitute this by this entire expression, which is there. Now, if you look at this will be like our A0x, if you want, A0x, because now we are dealing with function depending on x. This is a1x, which is a first degree polynomial, right? And now here, it's like 1 divided, we can take this in the denominator, but it will be cumbersome, so we can keep any fraction there, a fraction or constant term that doesn't depend on x, right? We keep it there in the numerator. And this is like our a2x. You can see that all these a0x, a1x, a2x should be a polynomial of degree at most 1. Or we can say polynomial of degree less than or equal to 1. Right. Okay. So that is it. Once this is understood, you can apply that to any other rational function. Now, coming back to the Padé approximation of f of x equal to ex, that is exponential. If you recall from the last computation, this is what we obtained. Now, if you perform the continuous fraction method that we just saw, you perform it to this, and this is exactly what we will get. So this is our a0x. A0x 1 by, as I said, 1 can be a rational number, not a function of x. Because if you want to make it 1, you'll be dividing throughout, and it will make your computation more complicated. So if it's 1, not 1, it's still the final answer will be the same. You can multiply the numerator by the reciprocal of this throughout, you still get the same result. So this constant doesn't really matter. Okay, so this is your a1x, and this is the denominator here is your a2x. Okay, now if you recall from what we mentioned above, we saw that in terms of computation, this is what we found. For this expression, we saw that the total number of multiplication was 9, and the total number of addition is 5. 1, 2, 3, 4, 5, because subtraction is a form of the addition. So let's copy this. Oh, sorry. Unfortunately, I have to scroll all the way down. Okay, so okay, so let us maybe here. Good, so let us keep it there. Okay, so we saw that if we count the number of the total number of multiplication, numerator and denominator, it gave us 9. If we compute the total number of addition, it gave us that. But if you take the nested form of the numerator and the nested form of the denominator, in terms of number of multiplication will be 5, the number of addition will still be 5, because in the nested form, number of addition is equal to the number of multiplication. Okay. Now here we have performed continuous fraction. Now let us try to compute the number of addition, because that's what is really costly. If you try to look at the number of multiplication, we just look at where x is present, right? That's where we compute the multiplication, because we look at the presence of x, right? That's where we compute the number of multiplication. Now, if we compute here, we can see we have 1 multiplication here. Sorry. We have 1 multiplication, 2 multiplication, 3 multiplication. So you see that in total, we have 3 multiplication. Now, let's look at the nested form. If we were to just write the nested form of the numerator, nested form of the denominator, you see that here we have 5 multiplication instead of 3. You see that continuous fraction gives us less multiplication. So, and addition multiplication is part of what we call the number of floating point operation. If it is high, it means that the computational time will be increased. So that is the application of continuous fraction. Why do we perform it? So we will stop here. And next time we will continue with the Chebyshev polynomial. So thank you so much for your kind attention. God bless you, and see you in the next section. Bye-bye.